Okay, hi everyone. Today I'm going to be talking to you about timescales of continental crust formation and our current interpretations of a garnet-lutetium-hafnium geochronology dataset from the Ivrea-Verbano Zone. So before I get deep into the study, I just want to lay out the framework for our motivation for the study. So we typically think of the continental crust as being chemically stratified into an upper, middle, and lower crust. And you can see that in the crustal schematic with Rudnick and Gauss estimates. However, when we look at exhumed granulite-facies terrains that are interpreted as being lower crustal, we see that a large proportion of them are much more silicic than expected. You can see that here in this histogram of granulite-facies silica content. These felsic areas of the lower crust are important because they'll control the overall strength and rheology of the crust, because they're weaker than their more mafic counterparts. And as these felsic sections are mostly comprised of metamorphic sediments, the main question here is, how are sediments incorporated into the lower crust? So an excellent locality to investigate this question is the Ivrea-Verbano Zone, a 100+ kilometer long, 14 kilometer thick section of exhumed continental crust, bounded to the northwest and southeast by alpine faults. And then gravity data indicates that the moho lies directly under the northwestern part of the section, the base of the section. And because of that, the Ivrea-Verbano Zone has been described as an archetypal continental lower crust section and has been investigated for decades. There are two main lithologies in the Ivrea Zone, the first being metamorphosed sediments, which are the pale green and yellow on the map. And then the second major lithology are mafic intrusions, including the large Mafic Complex in the southern part of the map. Metamorphic pressure temperature conditions are fairly well constrained in the Ivrea Zone, so the structural top of the section lies to the southeast, and that saw peak metamorphic conditions of about 650 degrees Celsius and 4 to 6 kilobars. And then as we move to the northwest, we increase pressure and temperature, and the base of the section saw temperatures over 900 degrees Celsius at about 10 to 12 kilobars. There have been a large suite of uranium-lead studies done in the Ivrea Zone, and a zircon uranium-lead date of 316 Ma is often cited as recording the timing of the onset of regional metamorphism in the area. So while there have been a large suite of studies done in the Ivrea Zone, there are still some key uncertainties that exist, such as the Prograde metamorphic path, which is necessary to constrain the mechanism of sediment addition into the lower crust. And then there are also questions about whether the field gradient that's preserved is a true geotherm and what the timing of the regional thermal climax is. So to investigate this, we did a lutetium-hafnium geochronology study from 6 metapolitic samples that span the structural depths of the section, and those sample locations are marked with red stars on the map. We chose garnet-lutetium-hafnium because of its high closure temperature and also the ubiquitousness of garnet throughout the section. So first, I'm just going to describe the lutetium-hafnium dataset that we have. And the key point here is that the lutetium-hafnium dates decrease with increasing structural depth. So our shallowest sample gives us our oldest age of 311 Ma. As we move slightly deeper into the section, we get slightly younger, 293 Ma. We have 3 samples that cluster in the middle of the section from upper amphibolite through to granulite-facies, and they give ages between 275 and about 265. And then our deepest sample gives us our youngest age of about 239 Ma. Due to the sample's structural depth correlation with its lutetium-hafnium date, I'll be showing you this figure in the top corner of each slide as I move through each sample in more detail, just so you have it to reference. The y-axis is a sample's distance from the insubricline, which is the fault that bounds the base of the section. So the higher up on the y-axis the sample lies, the structurally higher it is in the section. Then the x-axis is the garnet-lutetium-hafnium date, and I've put the timing of the Mafic Complex emplacement in the gray bar, just so you have something to reference in the white space. So we're going to start with the shallowest sample. It's the one that gives us our oldest age, and it's the only one that preserves any prograde major element zonation. So this figure here is a calcium laser ablation map from a garnet in the sample, and you can hopefully see that there is prograde zoning or zoning in calcium in the sample. So we have a core that is lower in calcium, and then this high calcium mantle in this bright orange, and then moving to a lower calcium rim. And then there's also a distinct thin rim around the edge of the grain that is hard to make out in the laser ablation map. It's only about 30 to 50 microns thick, but we can see it in things like EPMA transects. We can use a pseudo section to get peak PT estimates out of the sample, fit pretty well with previously estimated PT estimates, about 6 kilobars and 650 to 700 degrees Celsius. But we can use Garnet isoplex to get a lot more information out of this. So Garnet core isoplex indicate Garnet growth initiating somewhere around 5 kilobars and 500 degrees Celsius. Isoplex from the high calcium rim give us higher pressures, about 7 kilobars and 550 degrees Celsius, indicating an approximately 2 kilobar increase in pressure during garnet growth. And then from that thin outer rim, we get much lower pressures from our isoplex, about 4 kilobars and 580 to 600 degrees Celsius. So we can pull these PT constraints from both the stable assemblage and the garnet isoplex together and produce a clockwise PT path with an increasing pressure on the prograde path. And the 2 kilobar increase in pressure we get from the compositional isoplex is matched by gas barometry using garnet core composition, core and mantle compositions, and plagioclase inclusions within the core and mantle. And this potential clockwise PT path could be formed by a mechanism such as burial. So what does this mean for our lutetium-hafnium date? Now I'm showing you the lutetium laser ablation map from the same sample. And you can see that lutetium is concentrated in the garnet core. It's the same part of the grain where we had that increase in calcium that we related to prograde burial. There is the thin rim to consider in our date, and we don't see a large amount of lutetium in the rim, but we can see it in other trace elements such as gadolinium, which is the other map on the screen. Due to garnet's euhedral edges with low pressure phases such as cordierite and the low pressures we get out of the isoplex from this sample, we're interpreting the rim as being a second phase of garnet growth related most likely to heating during Mafic complex emplacement. We do get a slightly elevated MSWD from the sample, just above 1, so the thin rim could be the cause of that. But overall, we're interpreting the date of 311 that we get from the sample to record the timing of prograde burial and an increase in pressure from 5 to 7 kilobars at the top of the section. If we move now to our sample from Val Strona di Postua, this sample is outside of the physical aureole of the Mafic complex. However, it shows evidence for reheating due to its emplacement. So this is a lutetium laser ablation map from the sample, and you can see that lutetium is concentrated in 2 sections of the grain. There's a high lutetium core that looks similar to the sample I just showed that we related to prograde garnet growth. And then there's also this secondary high lutetium rim around the edge of the grain. And this indicates that whatever lutetium-hafnium date we get from the sample would be a mixing age between the timing of the high lutetium core growth and then the timing of the secondary rim growth. And when we look at our isochron for this sample, we do see quite a bit of spread along the isochron and a high MSWD. We can bracket the spread along the isochron with an older isochron at approximately 300 MA and a younger isochron at about 290. And with this, 300 becomes the minimum age of core growth and 290 becomes the maximum age of rim growth. We know that the Mafic complex was in place between about 286 and 282 MA, and this fits pretty well with this age of rim growth that we have. And so we're interpreting this age of 293 MA to be a mixing age between prograde growth sometime prior to 300 MA, and then a second period of garnet growth due to Mafic complex reheating. Moving on to the three samples in the middle of the section that give similar ages, they also have similar garnet trace element composition or trace element zoning. So I'm going to be talking about them all together. And while I'm only going to be showing data from one sample, the principles that I'm saying will apply to the other 2 as well. So this is a lutetium laser ablation map from the upper Amphibolite-facies sample. And all 3 samples show the same enrichment of lutetium in garnet cores, moving to a lower lutetium rim. The only difference is that the maximum lutetium concentration in each sample decreases with increasing metamorphic grade from more than 75 ppm in this sample down to a maximum of 5 in the highest grade granulite. All 3 samples show the same core enrichment in lutetium, and this sample that I'm showing you here is the only one that has any kind of a secondary rim with slightly elevated lutetium contents, and this is also the sample with the highest MSWD. Garnet isomodes from all three samples only increase with increasing pressure and/or temperature, indicating that garnet grew on either the prograde path or at peak conditions, not during retrograde decompression. So we're interpreting these dates that we get from these samples as recording garnet growth prior to decompression. I will note that we do get one sample that's a little bit younger than the other two. However, this sample is from Val Strona, which has a much higher proportion of mafic sills than Val Strona, where the other two samples are from. So we're still interpreting this date as recording garnet growth prior to decompression, but with a continued period of heating into the sill emplacements in the valley. Finally, our deepest sample shows evidence for late fluid-mediated garnet crystallization. So the top laser ablation map is a lutetium map from this sample. And you can see there's a lack of zonation in lutetium, and we see that in other rare earth elements and almost every trace element as well, apart from zirconium and hafnium. So the bottom laser ablation map is a hafnium map, and you can see that there are these regions of really high hafnium that don't seem to correlate with typical garnet growth. And the only feature that they may be correlated with could be the cracks in the grain. The 239 Ma date that we get from the sample fits with uranium-lead dates that other studies have interpreted as being fluid recrystallization of zircon at this time. It's also shortly before the emplacement of the Ivrea-Mafic Complex in the far north section of the Ivrea zone. And while the Ivrea-Mafic Complex is about 20 to 30 kilometers away from the sample location, it's not unreasonable to have started to have hydrothermal fluids circulating through the base of the crust at this time. So we're interpreting this age of 239 Ma that we get from the sample to record the timing of fluid-mediated garnet crystallization or recrystallization. Overall, the garnet lutetium hafnium dataset records over 70 million years of garnet growth in the Ivrea zone. This would require really high lower crustal temperatures over a long period of time. And some of the most viable mechanisms for this would be a thinning or even complete removal of the mantle lithosphere over this time. And if we start to think about what a schematic model of the tectonic changes in the Ivrea zone could look like, it could look something like this. So prior to 310, our Shallowest sample tells us that there was compression in the area and crustal thickening. Sometime between 310 and 286, we switch from compression to transition, and we begin to thin the crust. We also begin to add some kind of basal heat flux due to some kind of lithospheric event. Between 286 and 282, we had the emplacement of the Mafic Complex while we're still thinning the crust and adding heat to the base of it. Our garnet data tells us that until about 260, we had garnet growing through the base of the section. So we must have been adding heat still. We also had localized sill emplacements through this time period. Sometime after this, we begin to cool the crust. The crust is still thinning as it transitions to Tethyan rifting, and we most likely had some kind of hydrothermal fluid circulating through the base of the crust at some time. So this would give us clockwise PT paths, and some samples close to the Mafic complex would have high temperature excursions during its emplacement. We would see that garnet and other minerals would continue to grow at younger times in the deeper samples, producing a field gradient that is not a true geotherm, which is what we've seen in our samples. And like I said, there are multiple different mechanisms that could cause these PT paths, such as depth-dependent thinning of the lithosphere or a lithospheric mantle removal event, and we can currently not distinguish between these mechanisms at this time. With that, I'd like to say thank you to everyone who's helped, and I can take any questions.
Nick. That's a great data set. Could you comment on the initial question? Maybe you sort of alluded to the sediments and continental crust.
Yeah, so what we can tell from our constraints is that something like burial would be the most likely mechanism for getting the sediments into the lower crust. We don't see anything like the high pressures that would be required for something like relamination.
Yeah, more comment. It's good to see somebody arguing that the field gradient is not a geotherm, because its idea seems to be pervading geology at the moment. Thanks to my ground. Draw a line the origins point and put like in PT all that a geotherm. So yeah, it's good to see. People ignoring that idea. Thinking about it.
Thanks.
Banana.
Could you clarify a little bit what you mean by fluid-mediated garnet growth?
I'm not quite sure what like the fluids could have come from, maybe from interactions with the mantle, but some kind of fluids that would have maybe lowered the temperature for the garnet forming reaction to allow dissolution and reprecipitation of garnet or something like that. I'm not quite sure about what kind of mechanism it would have been necessarily.
I have a very brief question, if it's okay. We're going to
Yeah.
just go over a few minutes. Could you go back one slide? It's okay. So related to the next question of coming back to the mechanisms, you have these clockwise PT paths in your diagram there.
Yeah.
But if you're kind of tracking the position of the spots, there's no real way to increase pressure because you're thinning the crust. This rho GH zone you have on top of you. It seems like you're going to get some of that spot on top of you each time, and yet you're invoking a kind of clockwise PT path with a pressure increase.
Yeah. So we do see pressure increase during at least garnet growth at the top of the section, which indicates that there was compression occurring at least before that early phase of garnet growth. And I've just interpreted that as continuing before. It is the first orogeny, so
Sure.
yeah.
But isn't that all
Compressing.
pre-310?
Yes. So I could have just drawn the top turn on the PT path, but I had interpreted that as
Sure. Okay. We'll move on to the last one.